In view of the faculty we're in, we can't use the word like art. Technology is so much more important. So I thought state of technology would be more sensible. So I thought I'd say a few things about research I've been doing, a few things about starting off with how some people see the future of robotics, and roughly the state of the technology of robotics, and then a few things about things I've been doing, because that's what I really know a bit about. So I'd say a bit about, I've done some research in sensing for robots using sonar, and as far as I know, I'm one of the few people in the UK who does radar for robots. It is extremely difficult and not advisable, but I think in a few years' time, radar will be quite useful for robots. Because, of course, with sonar, you send out a pulse, and you measure the time of flight for the pulse to be reflected back to the sensor. And the time of flight is, well, the speed is 300 meters a second or something like that. And in air, the speed of sound in air. But for radar, of course, it's 3 times 10 to the 8 meters per second. So trying to measure those tiny little time intervals of nanoseconds and picoseconds is rather difficult. TV is a very useful sensor, and we've done a bit of research using TV as a vision, which I'll tell you a bit about. Also important for robotics is mapping. There are various machines that exist in the marketplace where if you want to make a robot, make a robot work, you have the opportunity of buying the robot, mapping the environment you want to work in, typing into the robot what the map is, and hope that the robot will follow the map. The trouble is, if you buy a robot that does that, half the cost of the robot is in getting the technician to come along, map the environment, and type it into the robot. And then if you want to change the environment that the robot's working, you have to get the guy back, you have to wait a couple of weeks, spend another £1,000, and the guy will retype the map in. So we're trying to avoid that. We're only interested in robots which will do their own maps, make their own maps. And we're also interested in path planning, done some work on that. And then I'll tell you a bit about a few of the projects which have some rather silly names like Robocop, and there's a pigeon, and there's one called Cycler, and we made a policeman and some humanoids. So let's get on with that then. Well, this is the vision of the future as seen by Honda. Honda make the state-of-the-art robot, which is Asimo. That's the best robot you can buy at the moment. Well, at least you can't buy it because it's just too expensive and it's fairly new. But there is Asimo in the center. So the idea Honda have is in a few years' time, just around the corner, as everybody says, you will buy yourself a robot which will become part of the family and do all the dirty chores around the house. So this is the marketing stuff, so that's how they see it. It's not terribly serious, but I suspect Honda actually believe that the day of mass-producing cars is over and the next item that is on the list might be robots. So this is the state of the art in robotics to some extent. This is Toyota's humanoid robot, about so high, plays the trumpet, which you might think is a rather difficult thing to do, and in actual fact it's rather easy in robotic terms to make trumpet players. This is Waybot, made by Waseda University in Tokyo. This is not the state of the art, this is way back 1980 odd, but Waybot plays the electronic organ with his feet and hands and moves its fingers about 15 times a second, much faster than a human can. And even with a single, very old-fashioned, I mean, you can tell roughly how old this is from the size of the TV camera. That is the TV camera. Nowadays, it's no bigger than this or something less.
I did actually see Waybot in...
Oh, really?
In Scuba in 85.
Yes, 85, yeah.
Yeah, when I had the expo there in 85, so I saw it really was mid-80s.
So I'm a bit dishonest in a way saying this is the state of the art, but in terms of, it shows, I think, that the problem of, and Waybot reads the music and plays by reading the music. So in 1980 this was the state of the art, but it shows just how easy it is to do things that you think are difficult, and how difficult it is to do things which you think are easy, like walking. So it's taken another 20 years to learn to walk, beyond playing playing the organ. So this is Asimo, which, as I say, is the current state of the art. There are now two Asimos. There's one they don't show you, which runs. So Asimo walks, turn corners, will walk backwards, walk sideways, up and down stairs. And it's about so high, so the idea is if you buy one and it falls on you, it won't kill you. Which is probably good for sales and marketing, because you can get so much paperwork if you kill people. So P3 and P1 and P2, the prototypes that came before Asimo were all sort of 6'6" high, weighed hundreds of kilos, and would have caused you serious damage if they fell on you. In fact, there was a robot dog produced by a firm in the UK from some Formula One engineers, and the dog was about so high, and a child could ride on it because it was so powerful, and they wanted to sell it, but they couldn't get it past health and safety, because if a child had put their hands in any of the joints, it would have just crushed them, because the robot had to have joints which are so powerful in order to be able to carry. And if it had fallen sideways on a small child, they would never got any insurance. So sadly, it was a brilliant design, but couldn't get past health and safety. This is sort of the state of the art in military robotics. This is the Predator, the aeroplane the Americans used unmanned, and it's used originally for reconnaissance. So here is an infrared camera which can detect for the very tiniest infrared signatures. For example, if you drive a car quickly round a roundabout, it can pick up the tracks of slightly warm rubber that you leave behind, and that's from about 50,000 feet. So that gives you some idea of the sensitivity of these cooled infrared cameras. And in the top is the transmissions up to the satellite, which send the pictures back to the States. And so these were used in Bosnia to find Slobodan Milosevic, and used in Iraq and Iran. Not Iran. Well, perhaps they are. Probably they are. There's a slip. Yes. Oops. And now they're fitting them with missiles, and you may recall that there were some alleged Al-Qaeda people driving around in the Yemen, and one of these fired the missile, and they are no more. So the days of Asimov's 3 laws of robotics had long gone and dead. State of the art, sort of, in space robots. This is Lunokhod for Russian Mars rover. So just showing how clever it is at climbing over rocks. It might have been more sensible to go round the rock, but I suppose that's a good demonstration. In theory, everybody says you must have legged robots because they'd never be able to climb around rough terrain like this. The answer is, why not drive around it? Or the other answer is, in actual fact, you can drive over a rock, which is about 1.5 times the axle height, if you use one of these sort of complicated axle arrangements. And of course, there's the parabolic dish aerial to send the data back to the Earth. So I suspect that in future, only robots are going to be used in space. There's a sort of psychological benefit of having humans in space for the benefit of getting money for the space program, but really all the arguments are in favor of robots, particularly for going very long distances because of all the weight of equipment you have to carry for humans, oxygen and food and waste disposal and safety equipment and all that life support systems. And of course, these are very, very hostile environments. Even the electronics can barely stand the environments. In fact, people say, well, we must have been visited by aliens. I think if there was intelligent life in outer space, we'd see their robots first, because they're probably going to be clever enough to send robots and not other aliens, but anyway. So I'd say a bit about sensing. And sensing is a non-trivial, trying to get robots to actually do sensible things. I know lots of professors around the country say we're going to have robots that are more intelligent than us in 20 years' time, and if we're lucky, they're going to keep us as pets and so forth. I suspect this is, whenever we get, I'm thinking of Kevin Warwick, who I profoundly disagree with, but we often do TV programs together, and they say, well, here's one view and here's the other. And I normally say, well, once you've made a robot that can avoid chair legs, then you tell me how to make a robot that will be more intelligent than us in 20 years' time. Because I think one of the troubles is robots still don't avoid trail legs. And here's one of the reasons. This is our test laboratory we had. So if this is the room that we were in, and in the center of the room we put the robot and the sonar scanner. So the robot just sits in the room, single sonar, goes around the room. Every 5 degrees takes a range reading. And this is a graph showing what the robot thinks, where the robot thinks the wall is. So here it's accurately measured where the wall is. I should have just there. Here it's accurately measured the range of the wall. And what's happening here is the robot is saying, the wall is out here. This is because the range limit of the sonar is about 10 meters. This is the standard Polaroid sonar that everybody uses. So this is one of the reasons why nobody has made really good robots that will wander around real environments like this with chairs, chair legs, table legs, tripods and whatnot. It's my world where you always find tripods. I'm so used to tripods. So typically what happens is the sonar will only get an accurate range reading if, and only if, the sonar beam is at right angles to the wall in both planes, plus or minus about 5 or 7 degrees. Anything else, there's another one there, anything else, and the beam bounces off the hard surface, goes away, goes around, you get no signal back, and the robot says, that wall must be over 10 meters away, I'll go off from there, and of course the robot drives straight into the wall. So this is not only a fault, it's a dangerous fault. So typically what happens is you get a true reading at where the wall is at 90 degrees to the beam, here, and you get, because of corner cube reflection, you get a true reading at the corners normally. The trouble is, you may only get 1, or maybe 2 or 3, depending on the shapes of the corners and the shapes of the walls. So typically, if you were to put a robot into the center of a perfectly square room, you'd get 4 true readings at the 4 plane walls, 4 more true readings at the 4 corners. So if you were scanning every 5 degrees for 360 degrees, you'd have 72 readings, of which 8 are correct, which is not terribly good. The trouble is, it's worse than that because you don't know which 8 are correct. So this is the great. So everybody says, sonar, we must use sonar on the robots, but it is a serious problem. So I was interested in using radar, partly because I came from industry relatively recently, and I worked for Chubb Alarms, and we were designing intruder alarms and human detectors, things which would recognize humans, for very expensive installations. So back in the same room, I thought we'll put a radar in the middle of the room and do a scan, and this is simply a measure of the amplitude of the signal coming back. So this is not a range measurement yet. And you see, you get quite a strong signal back at the right angles again, and you get these are quite a strong signal back opposite corners. But you don't get the nice, tidy picture you'd like to see, partly because you've got all sorts of edgy corners and doors, and you've got window pillars and all sorts of obstructions spoiling your experiments. Now these are 10 dB per large ring. So you can see the difference in signal from the poorest, where the signal is bouncing off and going somewhere else, is something like 10, 20, 30, 40, 50 dB. So you've got to be able to make range measurements out of signals which are varying in amplitude by over 50 dB, which is what, 10 to the power 5, which is, etc., 100,000 to 1 in power. I shouldn't say in power. So before you even start, that gives you some idea of the size of the problem, even using radar. So we've also looked into vision, and this is what a lot of people do. This is, again, I try to avoid students doing simulations. I try to avoid students doing artificially created environments. I try to get them to do all the experiments in real environments. And this is the real corridor of my last but one university. I have to move on. Every time I make some horrible mistake, I have to change universities, you see, just like the marketing men do. So I've learnt from the marketing and the finance directors, who that seems to be the way to live. Anyway, this is a very strange. This is the University of East London, the corridor in the electrical engineering department. On the right here are student lockers. At the top there is a radiator. It's the first time I'd ever seen a radiator in the ceiling. The architects had not learnt that hot air rises, you see. Anyway, so there's a real corridor, and these are windows along here. So what we want to do is for a robot to work out from that image without any sonar, without any odometry, because odometry is pretty unreliable. Well, they're all unreliable, but anyway. Where it is, to avoid bumping into the walls, avoid bumping into people or cardboard boxes or whatever, and find its way to the end of the corridor and not go down fall down the stairs. So the first thing what we did, oh, and the other thing is, I want to say to you students, sorry, you can't use 4 £50,000 Spark stations. You've got to do it on a laptop, because if anybody's going to buy a robot, it's got to have a laptop in it, because that's the only way to get cheap computing. So you've got to invent novel, original, clever algorithms for doing vision processing. Just TV camera, digitizer, laptop. So the first thing we do is to do edge detection. So to try and find in that image any edges. And vertical edges are no use to us, horizontal edges are no use to us, so we take those out. So what we're looking for is the edges which hopefully will meet in the middle, which is the vanishing point. So if you can imagine, in any corridor you've got a line where the ceiling meets the wall, left and right. There's lines where the floor meets the wall, left and right. And if you look at the image, eventually they all meet at a point. So that's what we're trying to recover from that image. So get rid of all the redundant stuff and recover those lines. You can see, you can just about make out the start. You've almost got enough information there to find the vanishing point. But we've got to do some further processing. So looking at that image again and counting up the number of pixels versus the angle. So if you can imagine, what we do is we imagine we've roughly got the center of the vanishing point and sweep around, measuring the number of pixels at all angles. And as we go round in the polar angle, we get a strong signal, a large number of pixels at one of those two lines going downwards, another large number of pixels, and then we can see there and there that these are the other two lines, which have a rather more pixels than the noise. So it's quite easy. This is an easy way for a computer to pick out what are the significant lines. But you can do a cut. You can say, well, if we take the noise level here, we've got two really strong lines. And if we take the noise level for these two here, so we have to sort of adaptive type noise level, these are two other strong lines. So we've got the 4 strong lines, we're pretty sure, even though that's a pretty nasty image. We draw the lines in onto the first extracted slide. You can see that was these were the 2 strong peaks in that histogram, and these were the 2 weak peaks in the histogram. And you can do a little bit of mathematics to you don't just take the 4 angles. You know there's a little from your geometry that line should line up with that line most times. It won't always. If the robot is over to one wall or over to the other wall or skewed at a funny angle, these aren't straight lines. This just happens to be that the robot was roughly in the center and roughly pointing down the center. But you can take various bits of geometric information to help you put those lines onto the data. Then you've got your vanishing point, so you know exactly where to aim the robot. And if the robot's too far over to one side, these lines will be, the center will be in the same place, but the angles of these lines will tell you that the robot that it needs to move to the center. So it's not only the aiming point you need, it's how far away from the wall you are that you need. The other useful part of this trick is that if somebody has left a box on the floor, on either side. This will shift this line over, this number of pixels over. There'll be lots of pixels over here maybe, where the box is, and the vanishing point won't shift. Well, it will shift a little bit, but it will tell the robot to move across the corridor. So it doesn't just work in unobstructed corridors, it works if people are wandering down or even crossing the path of the robot. So that's sort of an overview of the bits of research we've done with sonar, radar and vision. And I thought I'd tell you a little bit about the work we've done with area mapping. Because as I say, for example, the chap Engelberger who started Unimation made a robot nurse. And the idea was he wanted to make a mobile robot. He wanted to find a market where it could pay for itself. And he decided if you could make a robot that was take away some of the drudgery work from a nurse, because nurses are relatively highly paid in America, and you could make a robot that could economically compete. So he made a robot nurse, but you had to type in the map of the hospital for it, and that's increased the cost and made it uneconomic. And one of the other problems it had was whenever a small boy saw the robot, it would walk up to the robot and stand in front of it, and the robot would move to one side and a small boy would move to one side. And this would work for 1 week or 2 weeks, but every now and again a new set of small boys would come in, and of course it made the machine uneconomic. But it was very largely the fact they used very expensive vision. They used a £40,000 laser rangefinder, and you had to reprogram it. If they'd made it self-programming, we like to think it had a much better chance. And if they'd got rid of the £40,000 laser scanner and used our vision system, well, we hadn't invented it that, but what we're trying to do is make a copy of their nurse, but an economic version. So to do that, we want the robot to be able to make its own map. That's the first thing we want, because you take the robot out of its box, switch it on, and off it goes. You don't have to force it. So here is the idea. Here is the robot, this red spot there, and the robot, the first thing your robot does when you take it out of its box, switch it on, is it rotates on the spot with its scanner and takes range readings. And what these are little dots that say, I've measured the range here, and the range to the nearest obstacle is at least 4. These are robot widths. And these squares can be any size, and there can be any number of them. So it's saying there's 3 robot widths there, so I've got 1, 2, 3, 4, 5, 6 clear paths, and the green lumps are obstacles, so I can't go there. And this is the robot, is the red thing. So a little ways on, the robot every now and again, every time it moves it moves in the direction of the greatest amount of free space, so the safest direction. So when it was in that square, it decided that there was, I don't know quite why actually, there was a good lot of free space that way. Perhaps that was the first, after it'd done its scan, that was the first bit of free space that was more than 3 robots long. So off it trundles in that direction, continuously taking range readings. And these sort of greenish blobs are the robot saying there's an obstacle, and these yellow blobs are the robot saying there is no obstacle. In fact, each of these are probabilities, because every time it makes a new range reading, it's slightly less sure or more sure that there's an obstacle there or not. And what we don't want is the robot locking up saying, well, I measured there was an obstacle there a minute ago and there isn't one there now. You don't want the robot to get confused. You just say, well, the robot to change its level of confidence that there's an object there. So the robot trundles around as it goes, and it has in its mind it must make a complete contained path so that it knows, and when those link up, it can stop mapping because it's got a complete map. So on both sides of it, of all its path, it has green dots which say, I cannot go there, and then it's got the complete map. So as it trundles along, it continuously scans its radar, its sonar, So with this one, we've got ones, because we can't really afford 16 radars, we scan the thing on a stepper motor. Not radars, I keep saying radars, sonars. So as it trundles along, it continuously updates its map of where the obstacles are and where the free path is. Now, this is not a simulation. If in a simulation you have a perfect sonar which knows the range in every direction. Now, the robot is saying, yes, I'm fairly confident here, but this is the unknown area. And unless the robot has definitely made a definite range reading, it doesn't put in its inner memory. So this is a real machine in a real environment. It's not a simulated one. So we found a way around this problem that you've only got 8 true readings in 72, and we know which are the 8 true readings. We've solved that one.
How would you know that the robot is in one of the squares?
How do you know the robot?
Which square is he now? The positions.
I mean, the robot only knows where it is in relation to the obstacles.
Yeah,
So
as I see, you keep updating. Isn't it?
yes.
So you come back into the same spot, say, after going once around. How would you know that?
I mean, it has a memory, so it knows where it's been and where it is at any one point, but only, I mean, it doesn't know whether it's north or south or in any particular building or anything, only in relation to the green squares. Is that the answer?
Then maybe you're using some kind of encoders or something.
Well, we do have a odometry on the robot, but for this experiment, we're just seeing, can it make a map? So it doesn't know whether this is 10 meters or 10 inches. It doesn't know anything about distances at this stage. It merely knows I have a list of things I can drive down, i.e. corridors, and a list of things I can't drive down, i.e. obstacles. So the robot goes along, and you can just see there it's detected this obstacle because at some point here it was at right angles to it, but it doesn't know anything about that area. So it's not... I've seen a lot of simulations where everybody assumes that the sonar is perfect, and in all directions it has accurate measurements of the range. And what happens is it just keeps on going, taking the path with the greatest, the longest free path in front of it, until it's got a complete set of green dots on the right-hand side and a complete set of green dots on the left-hand side. This is the table in the center of the laboratory. It's not a very optimized course, but we don't care. And so it starts off here, and it ended up there. And when it got to that point there, it said, I can stop now because I've got a complete map of the building, of the room. And this is how it does it. I thought, well, if I'm coming to a university, I ought to have an equation in the slide. Otherwise, the credibility that I lost doing Robot Wars will never be regained. What we're effectively doing is the robot divides the world into cells, which are one robot width, and the robot is saying, I've made a range measurement there, and that seems to be 5 meters, therefore I'm pretty sure there's an obstacle there. And then it moves on, takes another range reading if it happens to be in that state, and then it says, I don't think there is an obstacle there. So it changes the height of the cell, which is the height of a cell is effectively the robot's view of the probability that there's an object there. For the sake of the algorithm for guiding itself, it creates a boundary to its world. That boundary can be as big as the memory will allow. And these are some obstacles in the robot's path. And we're saying, look, we don't know where you are, but we want you to get there. So we're going to give you the instruction you've got to go to is you've got to go to this goal, the water carrier or whatever. And what we're going to do is say that the height of that is 0. The height of the obstacles, which are 11, they're just convenient numbers for the sake of the algorithm. And what the robot does is it trundles around, it finds obstacles and says, that's a definite obstacle. I'm going to make those 11. It's found 3 definite obstacles, and we've given it a boundary of 11, which is the same as the obstacle. And what the robot does is it has an algorithm which goes through each cell, averaging, doing a kind of clockwise scan and an anti-clockwise scan, averaging the probability that there's an obstacle there between the goal and the obstacle. So what will happen is obstacles will get high numbers, goals will get low numbers, and you'll get a kind of a set of numbers where you'll get a gradual increase in the set of numbers. So wherever the robot finds itself, or wherever the robot is at any one time, having made this map. So the robot made this map, we haven't given it to it. Wherever you put the robot, say there, it can find its way to it can find the best way to the goal by looking at the adjacent cells and saying which one has the lowest number. So if we put the robot here on the cell which has a probability of an obstacle of 8.2, it won't go that way because that's 9.7. It will look for the number, the cell with the smallest number around itself, and that's 6.8 because 6.8 is smaller than those two. So it goes to 6.8. It will then look at all the other cells around it and go to the lowest one. It's got a choice of two there. Let's take this one. And gradually it will go to the progressively smaller scores of probability that there's an obstacle there and get to the goal. This is quite a common, this sort of idea of dividing the world into a matrix is quite common. What tends to happen for some of the ones, why did we do it this technique when some other people do it the same way? This particular technique can result in, suppose you go from a high number quickly to a low number, and around that low number are higher numbers, and for example, suppose we'd got here and that was a higher number, you'd be stuck in what's called a local minimum and it won't get out. And this particular trick we got eliminates local minima. So we know it always goes to the goal regardless. It's very, very difficult to prove. So it starts off, the robot has they're all obstacles. We don't know yet. These are the genuine obstacles, but the robot doesn't know whether these are obstacles or not yet. But we have told it that, initially we tell it that's the goal. So this is visualizing what the robot sees in a sort of human type visualization. So if you imagine you've got a square rubber sheet, we give the obstacles, make them as projections, mountains on the sheet. We make the goal as depressions on the sheet. And what effectively the robot is doing, wherever it is on that sheet, it will find the path of steepest descent by itself. It'll be like a ball bearing rolling down the path of steepest descent. And it's not a very good diagram because there ought to be a little bit of a bow here, because the other advantage of this technique is the robot will always choose the equidistance between the obstacles, so it'll take the safest route. So if it's over here, for example, it will tend not to go close to this, it will tend to take the middle route. So that's a kind of optical visualization of what's happening. So we wanted to test this out in real competition, and there is a competition that I've been involved with the IEE for many years, since about 1980 or something, called the micromouse competition. And I always try to get my students to make micromice. And micromice, if you haven't come across the idea, are small mobile robots about the size of a grapefruit, which have to solve a maze, which is this big. So it's 16 squares by 16 squares. Have we got a micromouse maze here? Terrible, terrible. Right. Anyway, it's a good fun competition for final year sort of degree students. That's maybe MSc students or teams of students. But anyway, the competition is you have a start square, which is the bottom left-hand corner facing north, if that makes any sense in a system, and a goal square, which is always the center. This is 16 by 16, so the robot knows that it has to find the goal, and the goal is roughly 8 squares up and 8 squares in. And that's all the robot knows as it begins. And what the robot does is it starts off and it can know nothing other than when it gets, it's trying to turn right all the time or whatever. It's trying to solve the maze. And the trick is, you want to try and solve the maze without mapping the whole maze, because mapping the whole maze takes time. What you want to do is know you have the shortest possible path to the goal, even though you haven't solved, even though you don't know where most of the walls are. So you want a kind of a cunning algorithm if you can get it. You want to minimize the search time. So the robot in this case has turned right and gone down here and found this is a cul-de-sac. I wish there's a better word than using French. Dead end, thank you. I'm told it's no longer de rigueur to use French. Anyway, dead end. Right, so the robot couldn't know that because the robot can't look down. This is like a human being inside inside the Hampton Court maze, where you can't see over. Anyway, so the robot has taken, we hope, a fairly good path to the centre, and we should be able to work out whether that path it's found is the optimum. And the competition works by the person with the shortest search time combined with the shortest run time. So having found the centre, the robot then has to decide whether to go back the same path it took, to take a chance that there might be a quicker route back. And then usually when we're designing these mazes, being sort of academic sadists, we try and arrange that there's a long path that's fast with lots of long straights, and there's some short paths with ziggly bits where the robot is liable to crash. Because everybody likes crashes, don't they? So we tested out the algorithms on this, and we use this for a bit of fun as well. So this is a real micromouse maze. At the moment it's in my garage, but in this particular case it was at my last university, the University of Central England in Birmingham, in the think tank. And there is a mouse. So sometimes people decorate these mice. It's a fascinating competition, and I recommend it to you. This is the robot we made. This is made by one of my PhD students, and that's Maisie, and very slow. We just took some couple of stepper motors out of BBC computers, but that's the fastest university-made mouse in the UK. So we're sort of reasonably happy with that.
How fast is Maisie?
Oh, terribly slow. It's painfully slow, but... how fast? I mean, that must be 3 times as slow. It must be nearer a minute as opposed to the 7 seconds. Well, perhaps that's a bit unkind. Perhaps a minute to search and half a minute to come back. So yes, but I mean, you can sort of imagine. I mean, the very fast machines are using specially wound motors, taking sort of 15 amps. This is a stepper motor going, zzz, you know, it's just like a scanner, really. This is a robot we made. One of the students made the base. I mean, I did the radars, and there's 2 TV cameras and passive infrared detectors, and there's a radio modem to send the signal to a base. The idea behind this is that this is a robot security guard. So it has, I mean, everybody looks at the micromouse mice and say, oh, well, that's a nice toy. My children would love that. In actual fact, they're rather cunning, and nobody sort of thinks it's very good until you put it on a big machine. You put it on a big machine, everybody thinks, oh, that's terribly clever. There's a kind of a psychological thing about size. Better not go there. And the idea behind this is it's rather like Engelberger's robot nurse, except it would patrol corridors of any size in a warehouse, and it was sparked off by a factory that was near us in East London that made laptops. And they said they had the most awful trouble with people stealing memories, stealing microprocessors, and it was really actually damaging their business to such a bad extent, and they got in a firm of security guards which stopped the thefts for a while until the security guards found where these things were, and they went up again because the security guards, of course, are not that secure. Apparently some of these memories are worth more than their weight in gold. They're just so expensive for a given weight. So we looked at the idea of being able to patrol up and down a corridor regularly, detecting humans, because the radars are good at detecting humans. Sonar is, well, okay, avoiding walls. So really this was a test platform for student projects. So the students might put their sonars there, somebody might put passive infrareds there, and somebody put radars there. And it worked okay. And the idea is simply, if it detects a human, and the radars are quite good at that, they send the signal through the radio modem to a guy and send the pictures to a guy who's sort of asleep or reading The Sun or drinking tea or whatever. So we think we can get that down to below the cost of employing a security guard. That's the idea. This is another fun little project that for one of my PhD students. It's almost not worth mentioning, but I think it's a bit of fun. Many, many years ago, there was a psychologist called Skinner, B.F. Skinner, who spent many, many years capturing huge amounts of data about pigeons who were very good at vision. And they decided, I don't think it actually went ahead, but he suggested if you had a pigeon in the nose cone of a missile, you could use the pigeon to peck at the right thing to aim itself at the target, because pigeons are so good at recognition. So you just have 4 little guidance things. And they weren't the only ones. The Russians were doing similar things on the other side. They were using robot dogs with explosives to go and find tanks and blow up tanks. And it worked up to a point. The dogs recognized the tanks and went up to them to blow them up. The trouble was when they tried them in real life against the Germans, the dogs went for the Russian tanks, which because they recognized those, not the German tanks. It's rather there's this kind of a little feeling of I don't know, well, serves them right or something for using those nice animals in there. But anyway, there's a huge amount of data. Skinner wrote books sort of 4 inches thick with hundreds of bits of data on pigeon behavior, and nobody analyzed it, and it just got left. And Skinner's work became unfashionable, or even worse. And so what we decided to do was see if we could take all his data, put it into a series of mathematical equations and algorithms, put that onto an artificial pigeon, and see if the artificial pigeon behaved like a real pigeon in this type of environment. So then we'd say, oh well, right, we've done it. We've made an animal which is we've made a robot which is intelligent as a particular animal, not a very bright animal, but bright enough. And then there's another psychologist called Hull who invented 16 rules of pigeon behavior, and we thought, well, we'd do the same procedure and see if Hull's work matched up with Skinner's work and matched up with robotics. So that'll be rather fun. So that's a current robot project. I'm trying to get the guy to write up, but how you get people to write up short of actually tying them down and hitting them with baseball bats, I don't know. This is another little project we did just for well, not quite fun, to make money actually. We don't tell them that, but we charge them quite a lot for these robots. The Royal Society for Nature Conservation wanted to try to find ways of encouraging people to throw away less waste, to reuse waste, to recycle waste, and reduce the amount of waste you actually create in the first place. And they thought the idea is to go into schools and give them a lecture about recycling, which of course is infinitely boring, until somebody had the idea, if you get a robot to give the lecture, the kids will listen. And sure enough, this actually works. So these robots, I mean, they're quite clever. I mean, the heads move up and down, left and right, the eyes follow the lips, and the lips are synchronized to the message. So inside each robot is an MP3 player with a series of likely questions and likely answers. And they go into schools, and the bottles here are supposed to say, well, the robots are made out of recycled things like Coke bottles. Well, yes, right. They also wanted total reliability because it turns out that these robots are so popular, they booked up 6 months in advance. And if you say, sorry, we can't visit you, the robot is broken down, you have 200 kids in tears, which is not a good idea, so they don't ask you ever again. So anyway, this is, they had to have a big launch, and that's Michael Meacher, the disgraced environment minister, and the people who sort of involved with giving us the money. And so the idea was we make a lot of money with making these robots and servicing them. We charge a lot to service them, and that would give us some more money coming into the robots lab. But anyway, these have now been into how many, I can't remember how many thousand schools, but they've seen 750,000 children. And the children, I can't remember, key stage, blah, I can't remember these things, but children about that high will sit on a wooden floor in the gymnasium for an hour listening to these things and paying attention. I mean, we were very careful about getting the body language of the robot right, so it waves its arms and moves its lips in the right way according to the strength of the message. And it does eye contact, which I don't do because I'm too nervous. And it goes round and scans up and down, but not what's the word? Robotically. It does it in the way sort of humans do. So we took a lot of trouble to put into the robots a kind of a personality. And although they are controlled by a person, the person just sort of has you can't sit there with a long aerial and 2 joysticks. That wouldn't do. So the person has something about the size of a mobile phone or something like that, and 4 little keys which they can hold and they start the robot off, stop the robot at a reasonable point, but the robot has the personality, etc., to synchronize the arms, the eyes, the lips, and the voice, and sort of dance around and so forth in sequence. So it's actually, even somebody who knows about robotics, it's almost impossible to tell how the machines work, because there's a lot which is triggered by the MP3 player, some of it's triggered by the operator, and some of it's triggered by the personality program, which is very carefully modeled on what we've learned about body language. So that's a lot of fun. And that's worked very well, because some of the schools, somebody has done an audit on it, and of all the schools that Cycler has visited, and of those schools, they've had a 47% reduction in the production of waste. And one school got it down by 97%, but that, of course, is obviously highly exceptional. So it does actually work. Another project we did was for the Police Federation, and this again makes lots of money for the robotics unit. So what they wanted, it was the Police Federation wanted to be able to persuade the party political leaders that police are spending far too much time doing paperwork and staying back in the police station when they should be outside. So the idea was they would take along to the party conferences a prison, put a robot in it, and the robot policeman would look robotic, sort of mechanically, sort of filling in forms. And it was to get busy politicians and media interested and get it into the newspapers, get it into the attention of the politicians. So they said, can you make a robot policeman which will look robotic? We don't want it too lifelike, we want it looking robotic. And this is what we made. So the holes there are for the voice to come out. It was too much to get the voice to come out of the lips when you've got all the mechanism for eye movement and lip movement and synchronization and so forth. And so it's a little bit too realistic, because it looks like a moving corpse, I think. And you think, is this dead? Is this a human that's dead or something? But anyway, it doesn't look too bad. So it was sort of successful in that there is the prison, and there is a robot and a politician. And the politician is Kennedy, Charles Kennedy. And so the robot appears to be reading from a script, looking up occasionally. The politician asks him the question, and he gives the appropriate answer, and the appropriate answer is given by the guy hidden in the crowd, which just has sort of 4 buttons. So sort of 90% of the robot's behavior is inside the robot. It's just that it's triggered, and everybody looks around and sees nobody with a sort of joystick and radio control unit. And a lot of people come up and think, I wonder how is that done? And then they end up with... and the message seems to have got through. I mean, they may have got through for all sorts of other reasons, but if it gets into the national press and the party leaders begin to get the message, then... And they're likely to do something if they think it's in the press. They won't do something. So the Police Federation were very happy with that. More recently, we've become interested in humanoids, and one of my students makes humanoid robots for a living, or at least he makes kits which he sells to schools and colleges through a firm called Milford Instruments, and in America through Parallax. So he designs these things, and he just about scrapes a living by making these. And it's he's really good at making humanoids, and I was interested in getting a humanoids sort of research group going. So I said, how would you like to have a free MSc or something like that? And he sort of got interested, so I roped him in. And it's very difficult to get a machine to walk. I mean, these look trivial and simple, and they will just, because they've got very big feet and the center of gravity is low, they will walk. And they can turn and come back, and they will bump into things and stop and turn and come back. All on a basic stamp. But it is difficult getting a machine to walk. And everybody thinks, oh, it's hard to make a machine play chess, but it's easy. And everybody thinks it's easy to walk, but it's hard. But anyway. Now another student, another chap I met who made this, which is a walker. In actual fact, it can run, and running is actually easier than walking, oddly. But anyway, when I was doing techno games, they said, well, we're running out of robots. And I said, well, let's see if we can get all the people who make humanoids walkers in the UK together. So we spent a few days trawling the net, and friends of friends of friends got them all together on techno games. And I asked them all if they would like to join a research group and maybe get a qualification out of it, and 4 out of 5 did, and this is one of the guys. So this is, he calls this mincer, because it sort of has very short sort of mincing steps. Have to be careful about that. So, and that works very well. The computing is off-board and arrives through that aerial, but all the power supply is on board, so it's not really autonomous, but he's managed to make a walker. In Japan, there's a competition to make robots sumo, but using humanoids as opposed to little wheeled vehicles. And it's a very popular contest. There's dozens of entrants, even though it's about £1,000 to make one of these things. And there was a chap in England who was making this to go to Japan. I said, how about coming along and being a student? And so this is his work, and I've sort of recruited him to join in. So this is the robot is in the way Japanese do. It's sort of bow before they kill you, as we were always taught in karate. And you can see from the large hands and the rather spiky implements that it's designed to do damage. And it sort of does the various karate moves. And if somebody knocks it over, it will get up. And somebody else who's a bit cleverer than this chap has managed to make one do handstands and cartwheels. I mean, it's non-trivial. Partly because these are radio control model car servos, and they really don't have the power for this sort of thing. And they're quite heavy, and the batteries are quite heavy. So to get a machine which has got all the processing on board, and the batteries, and these heavy motors, and you need about 30 of them, is really quite a challenge. So we hope to sort of get all that work together. And this works very nicely. You can see from the sort of scratches of blue paint that it actually has been in real combat. And it looks very real when it sort of does, yeah, sort of, that's the way these things do in Japan. And this is the 4th student I have who's into humanoids, and he does things very scientifically. He does a CAD drawing first before he makes anything. It's just, and this is the robot he made called Scarlet, and we got that on techno games. And this works quite well. 30 servos, 30 degrees of freedom. Well, no, there's actually 2 more degrees of freedom. Behind these homemade TV cameras and their lenses feeding onto an array of light-dependent resistors. And he is able to do some sort of balance control rather crudely, because when horizontals and verticals begin to tilt, even though you've only got 9 by 9 matrix behind the eyes, it's still sort of almost good enough to do balance with. But it does particularly good tracking, so if somebody swings a 60-watt bulb in front of it, it'll follow the bulb. So it walks, and if it bumps into something, it'll turn around and walk back again. And it uses this sort of blind man's stick to detect obstacles before it bumps into them with its detectors on the foot. It's got homemade balance sensors inside, three homemade balance sensors, and pressure sensors in each foot. So yes, there's some clever people out there who haven't got qualifications and should. So this sort of begins to signal the end, where to remind me that all these predictions of foolhardy professors and the science fiction writers suggest within a few years, within 20 years' time, we're going to have robots looking like that. Of course, it's easy if you're making a TV thing, you just get an ordinary actor and put talcum powder on him and say, right, we've got a robot. So that's easy, but everybody believes that this is really possible now. Well, not everybody, but people that high do. So these are the typical predictions of science fiction writers. It's much more difficult than that. But and what really saddens me about some of these predictions of science fiction writers is that by the year 2050, which is supposed to take place, they still haven't got a cure for baldness. That's it. Thank you very much.